We are living during an amazing transition. Artificial intelligence is coming, and artificial sentience will not be far behind. This transition will change humanity forever and create opportunities beyond our dreams. Powerful companies are spending billions of dollars trying to develop artificial intelligence. What is artificial intelligence? And how does it differ from an expert system? Understanding these concepts is vital to understanding the advanced systems that will soon help you navigate your starship through space. In the 1960s, a television program showed space travelers talking to computers almost conversationally. I remember watching these a decade later and listening to knowledgeable people argue that this would never be possible. Human language was just too complex. Machines could never understand it that well. But that 1960s show wasn't based on fantasy. The creator had gone to scientists and asked them, if you had almost unlimited technology, what is physically possible to do? At the same time Gene Roddenberry was imagining the future, NASA was trying to solve another problem. The Apollo program was planning to send humans to the moon, and no human being can actually fly a rocket. You can fly an airplane because your senses are able to keep up with the data input, and you can see where you are. You can feel changes in aircraft attitude and velocity. Even if you get lost in a cloud, you can usually sense up and down. The conditions of space travel are so extreme that none of these senses are adequate. When traveling from the Earth toward the moon, you could not trust your eyes to get you there, or your vestibular system to know which way you were pointing. If you took off from the Earth, aiming at the moon, by the time you got to where it would have moved, and the constant course corrections you made would have exhausted your fuel, leaving you stranded without propulsion, long before you got there. To travel in space, we have to improve our senses and be able to execute commands with fraction of a second accuracy. NASA needed a machine that would know where it was, where it needed to go, and what steps to take to get there. We call machines capable of carrying out complicated calculations a computer. But in the 1950s, the word computer was usually used to describe a person capable of carrying out complex calculations. Everything the Apollo missions needed to accomplish was worked out by hand on paper with slide rules, and double-checked with a few primitive electronic computers. This is one of the most humbling things about the accomplishments of the Apollo generation. Let's look at how this worked, so we can get a solid foundation for building an electronic computer. Here you see what we used to call a computer. This person has a proven ability to excel at mathematical calculations. This is the 1950s. And I have a rocket I want to launch to land me on the moon. I want to make sure I get there, and I don't trust my math skills, so I hire an expert. I give them an office to work in, so they won't be disturbed. This office needs to be comfortable for them, so I put an air conditioner in the window. And I want them to be able to work steadily, so I put a drinking fountain here and a vending machine, so they can stay energized. I install a small clock so we can track work time, and I tell them my goal. They tell me that they will need all of the specifications of my rocket system. That's a lot of information, so I bring them a file cabinet full of the technical manuals. They also need a textbook with all the relevant equations for rocket science. They tell me they will need notepads to jot things down, since they can't hold everything in their memory, and an adding machine, so they won't have to add and subtract longhand. They will need a journal to keep track of their progress, and I add an air tube system, so I can send them messages and make them aware of any design changes. And I want periodic updates, so I install another system so they can write a report and put it in a return tube, which will bring it to my office so I can read it. This looks like a good plan, and we have, in fact, built a computer system. By the 1950s, scientists were able to turn this into this. We replaced the person with a processor, called the Central Processing Unit, or CPU. This is an electronic general-purpose processor. It is a collection of logic gates, this big in the 1950s. While our person might use English and Arabic numerals, our computer can only think in ones and zeros. A string of 8 ones or zeros makes a letter, and a string of letters make an instruction. A general-purpose processor can follow whatever instructions we give it, but we need to load this processor with relevant equations. These equations don't change, and we had them in a textbook for our human, so we need to write these instructions on something permanent. This part of a computer is called the ROM. ROM stands for read-only memory. It is read-only so we don't accidentally change it. This is the equivalent of a textbook of equations, and contains the basic rules of processing information. This data stays if the power is turned off and reloads when it is back on. Nowadays we also have something called EEPROM, or electronically programmable read-only memory. This is used to hold instructions that need to sometimes be updated, like those for the CPU, that tell it how to do the basics. We also need a form of short-term memory. Any information in short-term memory will be lost if the computer is turned off or loses power. Our person used a notepad. We will use a random access memory array. These were, at first, electromagnets woven into a net. These are very tough, and ICBM launch control centers still use these in the 1990s. They were called plated wire memory. Here you can see what they look like, and here you can see them installed in a memory unit. This might have been up to 8K. Now that we can write to short-term memory, we need something more durable. When our person has completed a calculation, we can write it down in the journal, and these were again tape drives for pre-Apollo computers. For the instructions coming in, we get a basic keyboard, and for those going out, we get a monitor or printer. We replace the vending machine with a power supply, and the air conditioner with a similar cooling system. We get a much smaller, more accurate clock to time the computer. Finally, for the old adding machine, we install an arithmetic and logic unit, or ALU. This is a dedicated math processor. Now we have an electronic computer. This worked great if you had an entire room, but the Apollo engineers did not. They needed to shrink all of this down to something that would fit in a small spaceship. They came up with this. Here is the entire Apollo guidance computer. It is 61 centimeters long, about 32 centimeters wide, and a little more than 15 centimeters thick. It had a general processor with short-term memory. The short-term memory was loaded with basic function instructions using a type of string, with magnets woven into it. As these magnets passed through a reader, a magnet meant a 1 and an empty length of string with no magnet was a 0. These instructions would be loaded into the computer's RAM, giving it a base program. This computer had a unique type of RAM for short-term memory, to hold on to partial calculations until they were used. Then it could be rewritten for the next data set. These were ferrite memory cores that could be magnetized to make a 1 or demagnetized to make a 0. This could be reloaded with data if all power was lost. For communication with the human crew, they created a dual input display device that looked like this. This was the DSKY, or display keyboard unit. To ask the computer to do something, you hit a combination of these keys. Here is the easy-to-understand instruction sheet. There were specialized keys for each function. There were 2-digit displays for program number, verb, and noun, and 3 5-digit registers to display data on electroluminescent digits. Commands were entered in a verb-noun format. The verb is the action to be taken, the noun describes the data that should be acted on, and there was a button marked Pro to proceed with the calculation. Enter in clear or obvious, reset resets the program alarm, and key release releases control of the DSKY to the computer. But knowing what needs to be done and being able to carry it out are two different things. The scientists needed a machine capable of carrying out step-by-step instructions that could adjust to changing variables and make corrections when necessary. The ship must be able to sense its environment. We have covered space navigation instruments in depth in this lesson. Please take the time to review this important information later. For now, know that in space, a GPS or global positioning system will only work below the altitude of these satellites. Out in space, you will need to use something else. One of the most important things to know is exactly where you are when you start, and exactly what time it is. If you know exactly where you started, an inertial measurement unit will tell you if your ship moves. By measuring the acceleration felt by your ship and the direction of that acceleration, with the time over which the acceleration was felt, a computer can calculate exactly where you are. Then a starfinder is used to tell the orientation of your ship, which way it's pointing. The stars seem to move across the sky from our perspective on Earth. But that's because the Earth is spinning. Once we are in space, the stars would appear stationary, unless we are in orbit. Then the apparent movement of the stars would help track our changing position. And they are so far away that parallax, or apparent shifts in position based on distance, are almost negligible. So if we know where we have started from, and which way we are pointing, and keep track of how we move, we can calculate where we are. On sailing ships and even in airplanes, this can be calculated by hand, but not in space, where velocities and distances are so much higher that small inaccuracies would quickly get us lost. The suborbital Mercury flights didn't need a lot of navigation equipment. You know where it's launching from, you know how long the engine fired and at what power, and you can look out the window to see where you're going. An altimeter will help you track your altitude, and a compass can tell you which way you're pointed. A radio beacon with some ground stations can even pinpoint your position without GPS. This was fine until you get into orbit. Then your altimeter fails because it works on air pressure. And once you get into space, it can't tell you anything more. Your compass may not work well because of the electromagnetic fields created by all your electronics. So your inertial measurement unit becomes critical. To find their way to the moon, the Apollo astronauts needed to carefully track the ship's progress. They needed to predict where the moon would be in the future and fly to that location. This was all accomplished with the Apollo guidance computer and navigation equipment. Computers stayed in this basic format until recently. In fact, if you take the top off your computer, you can probably identify several components from what you've seen in this 1960s machine. Here is the central processing unit, short-term memory, graphics processing unit, long-term memory, fan and power supply. But these machines can only follow pre-written instructions. It does not learn from experience. Can we derive true artificial intelligence from machines like this? We can definitely build expert systems. An expert system has been programmed with instructions telling it how to respond to different events. You can program a large car robot to stop moving immediately if a warm bag of mostly water should fall in front of it. But for true intelligence, we need more. We need the ability to recognize unprogrammed events and make adjustments to protect the ship and accomplish its goal. Living brains do this by using something called a neural net. A neural net does not require specific programming. It does need a base code. For human beings, this is called instinct. Our base code tells us to find shelter, food, and a mate, to reproduce, and to run from dangerous stuff. Kids don't have to be taught to fear snakes. It is hardwired. Can we make machines that learn and mimic living systems? Tesla recently announced that they have started development on a humanoid robot. Just 2 days after I released a video suggesting humanoid robots for use on the Moon and Mars, I shamelessly went back and updated my thumbnail. This announcement was made on AI Day, where Tesla brings us up to date on their progress in this area. Tesla showed us their current computer system, featuring these dual Tesla-designed chips. For any space or car company to design their own chips is an astonishing undertaking. Chips are complicated. Here are the capabilities of this chip. We used to report capabilities of a chip by clock speed, and how many megahertz or gigahertz. This number told you how fast the CPU was cycling data. But this doesn't really tell you how fast the chip solves problems. A teraflop is a direct measure of a computer's processing ability. Specifically, its ability to calculate 1 trillion floating point operations per second. That means this chip can process 362 trillion floating point operations per second. Desktop PC chips can be a slow dual core at about 2 teraflops to a more powerful NVIDIA RTX GPU at 50 teraflops. GPU stands for Graphics Processing Unit. These are the chips that crunch the numbers to allow high-resolution game graphics. These are amazing chips, but the new Tesla chips have 6 billion transistors and are 21 times more powerful than the NVIDIA chips used previously. How are they able to do this? Let's look inside a Tesla system. Here we see a neural network processor. This mimics a living brain. A brain neuron makes thousands of connections with other neurons. Over time, these connections become stronger or weaker depending on the success or failure of the animal. If an animal is thirsty and heads toward an open field and finds no water, then turns back toward the trees and finds a stream, no one has to tell it to look near the trees next time. The memory of the trees will be associated with the need for water. The next time the animal needs water, it will look for trees first. This is called neural net learning, and chips with this capability can learn from experience. This is how Tesla cars improve their driving skills. Next, we see the GPU, or Graphics Processing Unit. This crunches the numbers to take the visual input from the cameras and break it down into a virtual world of edges, objects, and distance. This is almost exactly the way human vision works. Here's the main processor. It follows instructions like any good computer, while the GPU processes vision and the neural net learns by experience. There are safety features to prevent accidents and react to known threats like a battery fire, and also security systems to prevent hacking. Only Tesla code can run on a Tesla chip. The main difference between the Tesla car brain and a living brain is that every night your Tesla can download its neural net settings to a main computer, a type of hive mind. This hive mind will exist in an amazing new supercomputer called Dojo. Dojo is based on what are called neural processing units, and you can see one expanded here. Tesla automobiles have a self-driving function. Once you are on the freeway, you can double pull the cruise control lever, and your car will stay in its lane at the speed you set. It will slow down if the car in front of you slows and dodge most road hazards. But you must stay vigilant. Tesla Autopilot mode, and understand I think it should have been called Copilot, since the human should always be ready to take over, will release control to you if you have to take over during an emergency. When you take over driving, a report is prepared and sent to the hive mind. The hive mind will then see what went wrong and try to make a plan to deal with similar situations in the future. It does this by using neural net processing units to create an artificial cortex, to self-learn lessons from what the human driver does in that situation. This is the beginning of true artificial intelligence. The hive mind can then compare what all the cars have reported and send out updates to every one of them, so they all learn from each other's experiences. We are just scratching the edge of this technology. But just as Tesla has made a type of artificial cortex for vision, it can make the same for other functions, eventually even executive functions. The AI will be able to set goals, plan, adapt, and overcome obstacles, learn new things, and change its mind. These are all the result of neural net changes in a cortex, whether organic or synthetic. These functions will eventually be added to the onboard Starship computers. Human beings won't fly starships by throwing levers and pushing buttons. They'll give the Starship orders, and it will carry them out. Humanoid robots will have similar systems to explore unknown areas, perhaps deep in the lava tubes of the Moon or Mars, reporting back with perfect clarity what they find. These systems will automatically investigate unusual features and protect themselves from injury. What are the limits of this technology? How smart would you get if you could keep adding cortex? How much would you learn if you had 1,000 years of experience? But that's not all. Every new AI will be born knowing all the lessons of the AIs that came before. Where will this leave humans? Eventually, we will have artificial organs that last far longer than the ones we were born with. Over time, as our organic body fails, it will be replaced with a synthetic one. Then microscopic robots called nanobots will travel through our synthetic bloodstreams to our brains, inserting themselves into neurons, and taking over its function when the neuron dies. Over time, every neuron in the brain will be replaced with a synthetic one that can last essentially forever. You will not notice the change, since they will perfectly mimic your native neurons. But these synthetic ones will be able to download their settings to your computer system, a continuous digital backup, if you will. And should, after thousands of years of life, some accident destroy you, a new synthetic body and brain could be loaded with your mind, and a version of you would go on, learning and experiencing more of the universe. This is the future of humanity, if we can just last long enough to see it. Thanks for listening. Please don't forget to like and subscribe, and help us out on Patreon if you can, at Astra Protera.